Hi, and welcome to this lecture on Earth and Space Sciences. So they are just the fancy names for the scientific branches of geology and astronomy. So we're going to be having a look at some astronomical stuff as well as some geological stuff. So here are the learning objectives that you can see on the board. So if there is an exam for your course, then this is what I will be basing the exam questions on, okay? So use these to structure your study notes. If you can answer these, you'll be fine for the exam. So to determine the content, I went to the Australian Curriculum Science. I had a look at the Earth and Space substrand of Science Understanding strand, and this is what I came up with. So I got the content descriptors. I've highlighted and read the concepts, and then in the row underneath, I've actually named the concept there. So we're going to have a look at some astronomical events and renewable and non-renewable resources, because they're topics which are covered in Year 7. Year 8, we cover the topic of the rock cycle. Year 9, we get really into the meat of geology by looking at the theory of continental drift and all of the multiple lines of evidence which actually go into supporting that idea. Then in Year 10, we have a look at the Big Bang Theory, which is the organising framework within astronomy and explains a lot of the phenomenon there, as well as having a look at the matter cycles. So these are the concepts that you're going to have to get your head around if you're going to teach the Earth and Space Sciences strand well in junior secondary. So let's kick things off. Let's have a look at the seasons. Now, one of the great things about the internet these days is you're not just restricted to having students read paragraphs out of the text. You're not just restricted to going to the library and borrowing a video and having students watch that. You can actually have students interact more directly with the content. So I have a text here for you to use, and that text is a simulator. So let's go ahead and let's use that text. So I'm just going to come in here into the simulator, and then that's going to take us to, now I just need to pop out of here as well. Oh, we can see it. Excellent. Now, so if you're in here, actually I do need to escape out of here. So when you get into the simulation, it will look something like this. Now, if it does come up with here, make sure that you've got the Flash player installed. Once you click on that, and then you allow it, of course, it will take you into the simulator. Now, this is actually quite a good one, yeah, because you can actually play around with the actual elements. So you can actually move things around. You can, so for example, I can move the Earth to various places. I can see the sunlight angle as we move to various places. Now, what's also good about this simulation is that it gives you the two different views. So here we have, if you were on the ground and you were watching the sun transition the sky, and also if you're in space, because understanding the Western conception of seasons and one of the main driving forces in terms of determining day length and also temperature throughout the year is actually determined by phenomena that you can actually manipulate here. What's also good is that we can set the inclination to Venus and Uranus, so that's quite interesting as well. And you can do a whole range of things. So you can stop and start, you can make it go slow, you can make it go fast, you can change a whole heap of variables so that you can actually explore the seasons by yourself and not just have to read text. So this is what we would call a multimodal interactive text. So multimodal in terms that there are visual and elements, yeah, in this. So yeah, so definitely go through and have a look at this. So there is the interactive component. There's an introduction that if you want students to read that, they can as well. There's also some instructions on how to use the interactive. There's the interactive itself. And if you're a little bit stuck on lesson ideas, then here are some investigations that you can do and you can also get your students to do, and obviously the answers there. Okay, so do go ahead and use that simulation, because what I want you to do is to read that text and use this thinking tool, which is a table, to understand and record your understanding of the seasons. So we're going to use the Western seasons here: summer, winter, autumn and spring. Now that's quite different to the Indigenous season analysis that we've done in the lab. So rather than 4, there's a whole range of other numbers and a whole range of really complex epistemologies and ontologies that we're exploring in that analysis of the Indigenous seasons. But for here, what I'm going to ask you to do is to use that simulation and answer these questions, fill out these cells in relation to the 4 seasons. So we'll just take summer for example. I want you to record the height of the sun at midday. So imagine you're in the middle of summer. Where would the sun be? Would it be directly overhead? Would it be closer to the horizon, or somewhere in between perhaps? Talk also about the change in day length as you progress through summer. So is it getting shorter? Is it getting longer? You tell me. In terms of temperature, now this is a relative temperature measure. Is it cooler? Is it colder? Is it warm? And so forth. And also talk to me about the South Pole. Now, so during each of these seasons, which way, in which direction is the South Pole tilted? Is it away from the sun? Is it towards the sun? Okay, and that's going to be, and that's the driving factor when it actually comes to determining our conception of seasons in the West. And also, the last thing I want you to tell me is whether there are any special days. So is there an equinox in that season, or is there a solstice in that season? If you know the name of that solstice or name of that equinox, go ahead and name that as well. Okay, so use a simulation, complete this thinking tool to record and demonstrate your understanding, bring any questions to the lecture so that we can talk about it, we can dive in deeper. Okay, so just more generally, what's the big deal? Who cares about seasons anyway? Well, we've actually cared about seasons as a species for a very, very long time. Okay, so you can go to many, many places around the world, and our ancestors have actually built structures to actually record the passing of the seasons. So for example, Stonehenge is probably one of the most famous of these structures. You can actually observe the equinoxes and solstices, and that's one of its primary purposes was to actually mark when the midwinter solstice was. Because it was a time of great festival and gathering for people of the British Isles of that time. So lots of feasting, lots of sharing of ideas, lots of swapping of genes and reaffirming familial bonds, reconnecting with allies as well. So the tracking of seasons is really quite significant for cultures all around the world. So I'll talk about this one down the bottom here, Chichen Itza. So this is the temple of Kukulkan in Mexico. Now, what's really cool about this is what you can see here is that shadow as it is going down the stepped pyramid there. That's actually a snake head down the bottom. And at certain times of the year, I think it's the equinoxes, you can actually see the serpent god actually coming down to earth. So as the sun is rising and setting on that particular day, the shadow makes it look like the snake is first descending to earth and then ascending back up into the heavens. So that's a really cool phenomena that they built into that structure. Now, the Hamonga Maui, which literally translates to the yoke of Maui, is a structure which can be found in Tonga. Now, for a long time, we didn't really know what it was, but further investigation revealed it probably had astronomical significance. Now, astronomical significance in the fact that it was actually used to track the equinoxes and solstices, because they were hugely, hugely important to the early Polynesians. Okay? So the hamonga, now that can be translated into the burden or the yoke. Now the yoke translation is probably the one which is actually favoured, because that then directly relates it to a constellation, a Polynesian constellation called the Ha'amonga Maui. Now, where it is in relation to Western constellations is it lies within the Western constellation of Orion. So in this middle graphic here, you can see here are the stars of Orion, the Great Hunter. There's his bow here, and he's hunting Taurus in some ancient cultures. Well, in Polynesian culture, these stars here, these 4 stars here, they are actually the yoke part. So that's like this yoke part here, or over here in a strongman competition, there's also a yoke. So that I don't know, that 3-point structure there is known as the yoke, and it was actually an orientating constellation. So if you were a Polynesian navigator and you're out in the middle of the ocean, you would actually try and find this constellation, and it would actually tell you where north, south, east and west were. So it was a way to orient yourself. Now in this video here, I actually, one Christmas holidays, I went home and visited mum and dad, and I actually drove out to the Ha'amonga Maui. Now, so this was on, I think it was on the 21st or the 22nd of December, so right around the solstice, and I got there in the afternoon. And so, so if you were actually standing on top of the Ha'amonga, which you're not allowed to do anymore, but I was able to do when I was much, much younger, and you faced heading out to sea, you'd actually see the sunrise directly in front of you. So in the afternoon, when I was standing at the structure, if I turned around, I could see where the sun was setting. So this was right on the solstice. Now, it was hugely important for Polynesians, ancient Polynesians, to know when the solstice was, because it essentially signaled the starting of the voyaging season. That was when the winds had started to die down, the chance of cyclones was greatly reduced. So it was much, much safer to travel to other islands at that time of year. It was also hugely important because there were significant events to do with agriculture, and particularly with the planting of sweet potatoes and yams. So the Polynesian calendar very much relied on reading the stars to tell what time of year it was, but then the months were quite literally the names of a agricultural activity that you had to do. So there was a preparation of the soil, there was the planting, there was the waiting, there was the fallow, there was the seasons are named after key activities that you should be doing at that time of year. Okay? So it wasn't just those structures, and in ancient times we've continued to do that. And also there are some examples of ancient structures here in Australia which were very much about tracking equinoxes and solstices. So here, over here in Wathaurong country down in Victoria, there's up here there are a bunch of stones, and you would stand somewhere down here where the Y was, and you would use those marker stones to figure out what time of year it was. So it's essentially a large calendar. Here's a modern Stonehenge over in Esperance in Western Australia. So you can see nice neat cut stones, and here is one of those days. It would either be an equinox or solstice, so the sun rises directly between certain pillars. Here's one down in New Zealand and Wairarapa, and here is the New York's Stonehenge. So at certain times of year, if you stand at the right place, the sun is rising directly down that line. And here on the Gold Coast campus, there are certain times of the year when you're driving along Smith Street and in the afternoon, and the sun is right in your eyes as you're heading west along Smith Street. So you can almost consider that the Gold Coast Stonehenge. Yeah? Rightio, let's move on to another astronomical phenomena, or a phenomena that we can observe here from Earth, and that is eclipses. So again, there are simulations that you can use. So rather than drawing pictures on the board, or getting students to read a text, or getting students to watch a video, here is another option for you to spice up your teaching. These are simulations. So the way that I'd like you to demonstrate your understanding of solar eclipses is to complete this diagram. Now, this diagram, I just did a Google image search. It's from a website called Enchanted Learning. It's a great website. I definitely recommend that you bookmark that. So here's a labeled diagram. There's various elements that I would like you to label. So obviously there's the sun over there, there's the moon in the middle here, and here's the earth. But then there's also shadows and things that I want you to be able to understand and demonstrate that you understand. So we've got solar eclipse, and then we've got lunar eclipse here as well. So the simulation's there. Now, they're actually the same simulator. So I'll just quickly show you what that looks like by coming into the simulation. So this is it, and it's got the same kind of dual view. So, well, actually there's three. Yeah, so you've got the top view here, you've got the side view here, so you can press, I think, is that a play? No, it's not a play. Can we move? Yeah. Yeah. So you can move the moon around, yeah, and you can see what it would look like at various points like this. You can change the view between a solar eclipse and a lunar eclipse because they'll have different outcomes, and it's the same. Oh, look at this. Okay, so as we play, you can actually see what it looks like. Yeah, and this is one of the tough things that this simulation actually solves, is that having that multiple viewpoints to actually understand the phenomenon, rather than just having this top-down view or just this view from space or just this side view. It really gives students that full three-dimensional picture of what's going on. Okie dokie. So go ahead, complete those labeled diagrams, bring them to the lecture if you have a lecture. Excellent. Okay, so that is pretty much the section on astronomy done. Now, we've only really just covered two concepts there, seasons and also eclipses, but there are many, many other phenomena that you can actually investigate. Now, the phenomena that you investigate is sometimes will be determined by the textbook that you use. But if you end up teaching in a school without a textbook, then that decision is largely yours, what students tend to explore. Eclipses and seasons are kind of a go-to concepts, fairly foundational concepts for students to understand, but there's other phenomena that you can have students explore. And if you don't have a textbook, then you're a little bit more free. Or if you do have a textbook and you want students to explore other phenomena, then you can most definitely supplement. And that will be a decision that you and your head of department and the rest of the teaching team would make. So let's move into more earthly matters and look at renewable and non-renewable energy. Okay, so when we do have a look at renewable and non-renewable, we're pretty much talking about these categories of energy. Okay, now, so just to back up a bit, when we're talking about renewable and non-renewable energy, we're really talking about our meeting our electricity needs, meeting our transport needs, meeting our heating needs, and heating and cooling needs. So really what this is about is how do we get that energy to run computers, to go from point A to point B, to jump on a plane or to jump on a train or a boat and move around. How do we source all of that energy? So the two broad categories are renewable and non-renewable. So as the name suggests, it is whether the source of energy is either inexhaustible or is replenishable within a reasonable time frame. Okay, so they are the two conditions. Whether it's inexhaustible, such as the sun, well, for our purposes, it's pretty much inexhaustible. And whether it's replenishable, so the fossil fuels, that takes millions of years, it is functionally not renewable, not replenishable within human timescales, within planetary timescales, yeah, for sure, but yeah, definitely not human timescales. So let's have a look at renewable energies first. So we can get energy and we burn it and we generally turn turbines and then that creates electricity. There are 5 broad categories. So there are the solar energy, renewable resources. So we can either heat water directly. So if you've ever been camping and you've had that black shower bag that you go put out in the sun during the day and you've got hot water to shower with or cook with at night, that is one use of solar energy, solar thermal energy. Another use is photovoltaics. So that's where you rely on like high-end physics and where photons, they interact with the photovoltaic plates and generate electricity that way. So within each of these categories, solar, hydro, geothermal and wind, that can be broken down further into categories. Okay? So one of the things I would like you to do is to think about 2 or 3 examples for each of the renewable and non-renewable resources which kind of fall into that category. Okay? So for example, I've just given you 2 examples of solar energy. So see if you can come up with 2 or 3 for each one of these, renewable and non-renewable. Now the learning objective here is compare and contrast. So using your pre-existing knowledge, what I would like you to do is to use either a concept map or a double bubble to identify similarities and differences between renewable and non-renewable. So I've already talked about one of the key differences, and that is whether the energy source is replenishable or not. Okay, so generally, non-renewable energies are not replenishable on human timescales. Renewable energy are, as the name suggests, replenishable, or they are inexhaustible. Okay, so go ahead, complete that concept map, bring it to the lecture. Excellent. So moving on to the next topic. So that's around energy. We're moving on to the next topic and we're focusing more on the geology aspect, and this kind of relates to the grand theory in geology, and that's continental drift. So within continental drift theory, we conceive of the surface of the Earth, the crust, as existing as plates. So you can kind of think of it as, say, plastic plates floating on the surface of a pond, and they kind of move around, and sometimes they kind of bump into each other and drift apart. But what we've got with the Earth is that there are actually no gaps in between. Well, not obvious gaps, not big gaps certainly, and the plates are in constant motion. The reason why they're in constant motion is because underneath the Earth's surface is a layer of magma, and that is a layer of molten rock which is in constant flux, is constantly boiling. So what you can see here is a hot spot within the magma. So you've got the outer core down here, that's actually heating up layers of that layer above it, and all of that hot rock is less dense, rises, and as it rises, actually pushing apart those 2 plates up here. That's what we would call a divergent boundary. A plate boundary where the 2 tectonic plates are actually moving apart. Okay, so divergent meaning moving apart. So that's what causes those. Now a convergent is where 2 plates would actually be coming together. Now sometimes they will come together and they will buckle upwards. So you've got mountain formation. Sometimes they will buckle and one will get subsumed underneath. Okay, so that's where 2 plates are coming together. So we've got plates moving apart, plates coming together, and the third type of boundary is a transform. That's where you've got two plates side by side, and instead of one moving under or they're both pushing up, they're actually sliding past one another. Now, a good example of this is a San Andreas fault over in the US running down through to South America. So this is a plate over in California. And those in that region, the plates are actually sliding past one another, and that's why there haven't been earthquakes lately. But in California, it's quite a well-known area for earthquake activity. In fact, the whole Pacific Rim is known as the Rim of Fire, and that's because the Pacific Plate is in constant motion and butting up and jostling and doing all sorts of things with its the plates that it butts up against. And so if you looked at, say, earthquake activity and also volcanic activity, it's actually quite lit up around the Rim of Fire, around the Pacific Rim. Okay. Excellent. So let's look at a more local treatment of geology. And once again, this is where we are in one way addressing the cross-curriculum priority of Aboriginal and Torres Strait Islander histories and cultures. Now, histories and cultures, they do that in other subject areas. What we do in science is we look at the science. How did Indigenous Australians use their knowledge, their geological knowledge to go about their daily lives in Australia? Well, there are a number of ways that Indigenous people do that. They made use of the local geology in really, really quite interesting ways. So for example, ochres, so body paints. So there's evidence of trade of ochres, for example, up in Northern Territory, somehow making their way down to Victoria. Or there would be spearheads which that through chemical analysis we know are native to areas over in Western Australia, magically turning up in South Australia, for example. And so it's that kind of evidence, that archaeological evidence, that geological evidence coming together to indicate, for example, that there were complex trade routes crisscrossing all of Australia. But coming back to geological use, here are some common examples of the ways that Indigenous people use their geological knowledge to do a whole range of tasks, to perform ceremony, to make clothes, to hunt, to move around, to navigate their way throughout country, to grow crops and a whole range of things. Okay? So there are some examples that I want you to consider, and there's a bunch of links down in the notes of the PowerPoint of resources that you can access to complete this thinking tool, the table. Okay? So for each of those examples, what I'd like you to do is to tell me what type of rock form is it, what type of geology is being used here. Is it the landform? Is it the rock, as in the object that you can hold and do stuff with? Is it the mineral that's being explored here, or is it the mixture of soil? Okay, so have a good think about that and just pop that in the that rock form column, and then give me a little bit more detail. So for example, what were ochres used for? Can you describe the poking implements that were used? What were they used for? Cutting implements, what variety of cutting implements were used? Landforms, give me some examples of landforms and what those landforms were used for. Okay, so again, use the resources down in the notes section of the PowerPoint to find and extract information to complete this table. Okie dokie. Right. So in year 10, we start to look at the full variety of matter cycles. Now, when you look at the curriculum, the water cycle was specifically mentioned back in year 7, but the other matter cycles weren't mentioned until year 10. Now, as a way that you can have students explore this, is we're going to role model using the carbon cycle. Okay? So the carbon cycle obviously describes how carbon cycles through the various spheres. So there's the biosphere, the sphere which contains animals and plants. That's something you can pop into the table. The hydrosphere, that's the parts with the water. The geosphere, that's the land part, and the atmosphere, that's the air part. Yeah. So in the next slide, I'm going to show you some graphics and talk a little bit about how the carbon cycle works, how carbon moves through each of these spheres and the form of carbon as it goes through. Now, in terms of our understanding of climate change and the impacts of digging up geologically stored forms of carbon and lots of it and releasing it and shifting it from the geosphere into the atmosphere has important ramifications for the carbon balance and the energy balance of the planet, because a large part of the amount of energy coming into the Earth and the amount of energy leaving the Earth is determined by that carbon dioxide blanket that we're wrapping the planet in. Now, if we didn't have that carbon dioxide blanket, we most likely would not be here as a species. So yes, it is important, and yes, it is important for us to understand how this really, really important blanket actually works. Okay, so let's have a look at this representation here first. Okay, so for example, let's imagine that we are a carbon dioxide molecule in the air. So we're just happily floating around the air, and all of a sudden we bump into a leaf, and the leaf takes us in, and we head over to the chloroplast, and magically we found ourselves bound up in glucose. So now we've gone from carbon dioxide in the air to carbon in sugar form in a leaf somewhere, or in a fruit, or we're part of the wood, or we're down in the roots, or something along those lines. Okay, so just imagine where we've been packaged up into, say, a nice delicious nut. Well, animals come along and they either eat those leaves and they eat those nuts, and so they take the carbon which has been stored by the plant, taken the carbon dioxide out of the air, stored it in glucose form or some other carbonaceous form. We've come along and eaten it. Now, there are two ways for us to move on. So we can either get used up in the process of respiration and breathed back out, or we can actually stay inside the animal until it dies, and then we decompose. So we go from the biosphere, so the plant animals, bacteria, viruses, other living things all constitute the biosphere. So from here, we can either re-enter the atmosphere as a carbon dioxide molecule, or we can get buried. So millions and millions of years ago, huge forests, huge swathes of algae in the ocean lived and died and decomposed. Their decomposing bodies actually came down here and became part of the Earth. Now, given enough time and enough concentrated carbon, for example. So, for example, down in Victoria, many millions of years ago, just covered in these lush, dense marshes. So marsh plants, wetland plants, they grew and grew over millennia. Their bodies died and then settled down and formed all those masses of coal layers and coal seams which we mine down in Victoria. And the same thing up here in Queensland as well. So they have formed the Bowen Basin, the Galilee Basin, those huge coal seams that we mine up here in Queensland. So then those fossil fuels are stored over geological time, millions of years, and then we come along as humans, dig all of that coal up, all of that carbon up in coal form, burn it, and release it back out into the atmosphere. So that can come back out also through just natural geological processes, but as the arrows indicate, the major flow of geological carbon into atmospheric carbon is due to human influence, and a tiny part from geological. So the size of these arrows in this diagram here indicates the amount of carbon which is shifting. Okay, so another key thing to note in this diagram here is the color of the arrows. So these maroony reddy color arrows, that is where carbon is moving into the atmosphere in the form of carbon dioxide, and the blue arrows is where carbon is moving from the atmosphere into either the hydrosphere through a process called dissolution over here, into the biosphere through the process of photosynthesis, or into the geosphere through the process of death and decomposition. Okay, so the blue arrows indicate storage of carbon in either the biosphere, the geosphere, or the hydrosphere, and the maroon arrows indicate the move of carbon into the atmosphere. Now, this graphic over here provides a few more numbers and is a little bit more complex, so I'm going to leave that up to you, because this is going to be one of the key ways that you're going to help your students understand what's happening in terms of the amount of carbon dioxide and how we as humans are influencing that and driving massive global change through our manipulation of the carbon cycle. Okie dokie. So go ahead, describe the major components and the processes, bring that to a lecture. Okay. Excellent. So let's move on to the rock cycle now. Okay, so the rock cycle describes how rocks, which is mixtures of minerals from soil into solid rocks and back again, is described. So we've got three main types of rock. We've got the rocks which have been formed by fire, the igneous rocks, hence the word igneous, which has the same root word as ignite. We have sedimentary rock, the rocks made from sediment. And we have the metamorphic rocks. So these are the rocks that have been changed. They've been changed either by lots and lots of heat, or lots and lots of pressure, or lots and lots of heat and pressure. Okay? So what this diagram elegantly does, I'll just go back, what this diagram elegantly does is it summarizes the transition from one type of rock to another and names those processes. So this is really a visual representation of a paragraph. Okay, so I'm going to read it to you because it's a concept map. Yeah, so we've got sedimentary rock. So here we go. So sedimentary rock, when you apply heat and pressure to that can change into metamorphic rock. Now, if you get metamorphic rock and you shove it all the way down into the earth and you melt it, that becomes magma. Now, that molten rock, magma, if that's allowed to cool, then that can crystallize into igneous rock. Now, igneous rock, again, if you apply heat and pressure, that will turn it into metamorphic rocks. But if that igneous rock, so for example, in basalt or say granite, for example, up in Bundaberg or down here on the Sunshine Coast or up here in the hinterlands of the Gold Coast, there is a lot of volcanic rock. There's lots of granite. The granite belt in Queensland, Stanthorpe and so forth, is called the granite belt because it was once an old volcano. So that igneous rock, as it weathers and erodes, that produces really rich soil. So if you have a look at some of our most rich farmlands in Australia, they are found around volcanic regions. So Bundaberg, there's a hammock, which is an old and extinct volcano. As it eroded over time, produces wonderful red rich soil that local farmers and Indigenous people have actually utilised over centuries to grow really good crops. Same thing down here in the scenic rim, which is another large food bowl. The Sunshine Coast, up around the Glasshouse Mountains, another area of rich farmland, simply because it used to have volcanoes. as that rich, mineral-rich rock eroded over time, produced sediment, and that sediment we use to grow crops in. Now, sometimes if that sediment is actually collected and you pile it up enough, so for example, rivers transporting sediments from the mountain down to the beach, if we compact and we cement that all that sediment, then it can actually turn into sedimentary rock. So for example, here in the southeast corner, we have some really, really rich sandstone deposits, generally up towards Toowoomba. That's because there were huge drifts of snow, more than likely coastal regions at that time, that a whole heap of sand banked up and got squished and became sandstone. Then we used that sandstone to build a lot of the buildings in Brisbane, for example, all of the nice ones. And also UQ as well. So a lot of the sandstone at UQ was actually mined out Laidley way. Okay, excellent. So we're going to get to the granddaddy of the ideas within geology. Okay, and that is the theory of continental drift. So this was Wegener's idea back in last century, that essentially he came up with because he looked at the world map and realized, hang on, if I look at Africa and the Americas, they kind of fit together. I wonder if there's something in that. Well, that was in his grad days, and eventually that turned into a full-blown theory. So what I would like you to do is to watch these two videos. So to watch the videos, you've got to download the PowerPoint from the team site, put it into presentation mode, and then they become active. Then you can just go and watch the videos, okay? So watch these two videos, and what I want you to do is just to write notes. So I've been giving you thinking tool after thinking tool so far, but for this activity, I'd just like you to go back to traditional note taking. So just take dot points, okay? So bring that to the lecture. We can talk about that a bit more. So the thing is with theories is that we need evidence, and not just ideas or hunches, but actual physical evidence. That's point number one. Point number two is that for a theory to really demonstrate its rigor and how correct it is, what would be really helpful is that if a theory had support from multiple lines of evidence. So for example, the theory of continental drift, which is a geological theory, it would be nice if there was evidence from, say, biology, evidence, say, from chemistry, evidence, say, from physics, that supported that idea that the plates were actually moving around and bumping into one another and doing all sorts of things. Well, it just so happens that there are these multiple lines of evidence which support the theory. So one of these is the fossil evidence. Now, when we rewind the clock, so we know that plates are moving around, butting into each other and floating apart, doing all sorts of weird and wonderful things. So based upon how we know the plates are moving today, and they're kind of moving in a certain way, well, if we press the rewind button and we move it backwards, then we find that at one stage in Earth's past, then there used to be this great southern continent known as Gondwana. Now, Gondwana was made up of pretty much the current southern continents of South America, Africa, India, Antarctica, and Asia. So well before India started butting up into Asia. All of these current continents were joined together into one mass called Gondwana. Now, when we have a look at the fossil record, so when you go to South America, for example, and you go to Africa, you'll find that you can go digging in the rock and find a fossil, something which looks like a crocodile, not only in the bottom of Africa, but also, weirdly enough, over here in South America. And we know that it couldn't really have gotten from South America to Africa in today's arrangement of the continents because it is a freshwater animal. This four-legged land animal here, we find through Africa and South America again, cannot swim across that distance. This animal over here, there's land reptile, which we know not to be able to swim. We find in Africa, Madagascar, India, and also in Antarctica. And so this is its distribution here, okay? And then the same thing for plants. So it's not just animals, but it's plants which actually show this relationship as well. So the only way that we could, as scientists, get it straight in our minds that the fact that we find, for example, this fossilized plant through Australia, Antarctica, India, Africa, and South America, the only way that we could actually make sense of that, the hypothesis or the model which makes the least number of assumptions, is this idea of continental drift. That when we apply continental drift, we rewind the tape, we go all the way back to Gondwana. The only way that we can reconcile the distribution of all these fossils is by using continental drift. So not only is it the fossil record, but it's a whole range of other things as well. So there's biogeography. Okay? So there's the fossil record of things which were once living, but there's also living examples that show that once upon a time the land masses were combined in this continent called Gondwana. So when we have a look at the ratites, the large flightless birds, so we've got the rhea over in South America, ostrich in Africa and Australia, we have the emu, Papua New Guinea, and also Australia, we've got the cassowary, and in New Zealand, we've got the kiwi. So the only way that we can reconcile the appearance of these flightless birds on all of these continents is to, again, apply continental drift theory. Same thing with these plants. So the proteas, we've got the Australian waratah, the protea over in South America, South Africa, macadamia. They're all related genetically, and that's because they came from the same source. Their ancestor lived on Gondwana. And the same thing with marsupials. So marsupials is one of the first experiments that life had when it came to these new kind of animals called mammals. And the marsupials first evolved on Gondwana, and that's why we see them in not only South America, but also Australia. We see them in the fossil record, but we also see them in living animals. So we've got the opossum over in South America, and we've got the full suite of marsupials here in Australia, okay? So, some further reading. Now, one of the things which comes up time and time again in astronomy is, how did the Earth form, or how did the solar system form? Well, luckily for you guys, there is all of that information out on the internet, and you can quite literally just type your question into Google, and then it will give you one of the top results will invariably be a YouTube clip. Okay? So there's stuff on YouTube which you can definitely look up. What I also recommend that you do is that you start to get to know reliable sources. So this one here is Minute Earth, and I'm not quite sure what that one is over there on the left, but it is it's actually correct as well. I'll have to check up on where that actually came from. Okay, rightio. So that's the big theory in geology. The big theory in astronomy is the Big Bang theory. So this is the theory that that the universe actually started with the Big Bang. Okay, now it's kind of Big Bang was really just the name that they came up with to make it sound sexy, but it actually wasn't a bang of any sort. It was just a really quick inflation and a bunch of other stuff. Okay, so what I'd like you to do is to introduce you to the Big Bang theory. Here's a video by Kurzgesagt. So Kurzgesagt is going to be one of those go-to authors that I can highly recommend. So go ahead, watch that video. So the thing with theories, so just like continental drift can explain why we see plants that can't swim on different continents, why we see fossilized animals on different continents who obviously can't swim, living examples can explain, continental theory can explain why we see living animals where we do. Well, the Big Bang can do the same thing with astronomical phenomena. So go ahead, watch this video and just list the variety of phenomena that the big theory can explain. Okay, so there's a fair few concepts and a fair bit of independent work that I'm going to ask you to do, some groundwork I'm going to ask you to do, because it's in doing that groundwork, in wrestling with the content, making meaning with the content yourself, that you're able to identify, oh, hang on, I don't know about this concept, or, oh, I'm still not quite clear on that. What you're doing is you are using your metacognitive skills to identify your strengths and weaknesses in your current knowledge base. Once you've identified those gaps and deficiencies, you make a note of those, and then you come to the lecture or the workshop or the lab, and then we address those directly. Okay, so that way the learning is more student-centered, because you're building the foundations, you're identifying the gaps, you are bringing those gaps to me, and we are working together to help you fill in the gaps and to build upon your knowledge base. So here are likely questions on your exam, if there's an exam in your course. Okay, now just a couple more things, some extra material that didn't couldn't make it into the lecture proper. But if you're interested in the Indigenous astronomy aspect, then here's an article that I found, and there's a whole bunch of work, really interesting work done by Hamacher, I think his name is. He's an American. He's really interested in Australian Indigenous astronomy, and he's done a whole heap of work working with Indigenous people such as Uncle Bill here, in terms of recording that story and getting that really important Indigenous knowledge into the more general astronomical knowledge, and it's just really enriching our understanding of astronomy. And also the Pleiades, this also wasn't able to make it in the lecture, but just to show you how astronomy is a field which was of concern to people all around the planet. So the Pleiades is a great example. It's one of the most easily identifiable constellations in the night sky, and it was known to many, many ancient people. So in Japan, it's known as Subaru. So the company Subaru, that's actually the constellation of Pleiades. The Seven Sisters, Japinga, here is a representation of it. There's a hotel in Brisbane City, I forget what it is, but that has a painting of the Pleiades as well. The Pleiades, or Matariki to Maori, was actually an important constellation because it was a time marker of the year. And also here in southeast Queensland, and the Gold Coast in particular, the Pleiades was important in the Yugambeh tradition. So the Pleiades to the Yugambeh was Durin, the snake. So there's a whole range of different representations. Oh, even the Greek as well. That was a really interesting myth that exists about the seven daughters. And so there's stories about that in Greek mythology, there's stories about the seven sisters in Indigenous astronomy. That kind of idea, that constellation, is all around the world. Okay? Thank you very much.